So now we can figure out what is the frequency between the, say, if between, say, two different energy levels, then it's going to be given by ME4 divided by, I think, okay, let's see. So if I just go to this formula, where's this, my formula? Here, right? So this is the, copy this and paste. So for a general, for basically for some value of n, we will have 1 over m squared and then minus 1 over m squared. Okay, so essentially this is going to be the formula that gives the possible frequencies of the hydrogen atom for values of n and m, which are given by integers. Okay, is that clear?
Yes, sir.
So there are these series that were discovered before Bohr came up with this, picture, and the Bohr atom nicely, explained this series. And what are these? So essentially, if you plot n in the y-axis, so this is n. Suppose this is n 10. This is 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So yeah, so we have 2, 1. There is no 0, of course. Okay, and then there are all these series that you can. So there are all these different transitions now. So the transition to the lowest level from all these different levels, so these ones, so the transitions to all the lowest level, that's called the Lyman series. And similarly, there's going to be the transition to the second level, and I'm not gonna, those are known as the Bohr series. And there are a few others, okay? So these are named after people who found them through experiments. So here, of course, in the y-axis, I have given you a linear scale in n, but if we map it to the energy scale along the y-axis, then it's no longer linear. Then if this is 1, n equals to 1, and then this is n equals to 2, and then n equals to 3 would be something like this. So this is En, and these are n, 3, and then 4 would be here, and 5 would be here, 6 would be here, blah, 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 blah. Okay, and there would be infinity here. Okay? So this is basically what, was a spectacular success, but the Bohr atom had some issues. Okay, so for example, number one is that the non-radiating orbit seem ad hoc. Okay, that's not very serious, but the more serious one is that it failed to describe the relative intensities, okay? Relative intensities of the different lines. And while you can improve on that by going to an elliptical model, it actually doesn't, solve all your problems. The other thing is that, it doesn't even do a good job number 3 is that, doesn't explain the helium atom well. Okay, so so after hydrogen, the helium atom is the simplest atom that we know of, and it even fails to explain the helium atom well. So something else was needed, right? By the way, so Schrodinger equation is much better at explaining those things, even though in cases even more complicated than the helium atom, we can't really solve it exactly, but we can do a numerical analysis. But even Schrodinger equation for the very heavy atoms, such as, say, the gold atom, Schrodinger equation actually it fails. And the reason is that gold atom has lots of electrons. And if you think of classically, the outer shell electrons, they determine the chemical. No, if you think quantum mechanically, the outer shell electrons, they determine the chemical as well as the optical properties. A lot of the optical properties of gold. And a heuristic way, the outside electrons should have a lot more speed and velocity than the inside electron. For an atom like gold, the outside electrons are so far away and their speeds are so high that they actually, a relativistic treatment is actually appropriate. But the Schrodinger equation, is not a relativistic equation. So if you solve the Schrodinger equation, if you try to solve gold using Schrodinger equation, you find that the gold doesn't have its sheen. Gold looks like it's lead. So the fact that gold has the shine is a relativistic effect. Okay. So anyway, that's beyond the scope, but I wanted you to know. This is something that a friend of mine from he also studied in Dhaka University with me, but he's now an atomic and molecular physicist, and he told me about this. All right, so this is it for now. Oh, I wanted to give you the RID. I'll give it to you some other time. Do you have any questions so far?
No, sir.
Okay, anyone else? Sorry, I've been very busy. But I will get to the posting the lectures and I will catch up. Okay, so.
Sir, you said the Schrodinger equation cannot explain the gold atom, right?
Yeah, the outer orbits of the gold atom. Yeah.
So is there any new model that can explain after Schrodinger model?
Yeah, of course. The Dirac equation is a relativistic equation.
So that considers the special relativity stuff.
Exactly, but the problem with the Dirac equation, it's not a problem. It just it leads the doorway to quantum field theory. The Dirac equation says to us that the number of particles in your system may not be constant. If you have some energy, that energy can get converted into particles because E equals to mc squared. So relativistic quantum mechanics is a if when we talked about statistical mechanics, we saw that you can change the number of particles in a system by playing with the chemical potential. And you can do that sort of things even in non-relativistic quantum mechanics, but it's something not natural. Quantum mechanics itself doesn't tell you, quantum mechanics doesn't tell you several key important facts. By quantum mechanics, I mean the Schrodinger non-relativistic quantum mechanics. One of the key facts that it doesn't tell you is, when are you going to have, when is the number of particles not going to be conserved? The other thing is, it doesn't tell you why different particles of same type, say electrons, have the same mass, or why they are exactly identical. That is not something that quantum field theory, that quantum mechanics is able to tell you. For that, we have to go to quantum field theory. So the identical nature of particles is built into the framework of quantum field theory. Okay. So, but that's something we don't really teach quantum, although there's a quantum field theory course at BRAC and at undergraduate level. It's really a graduate level course. Okay, so any other questions?
So there is a theory that says every electron in the universe is the same because they're the same electron. What do you think about that?
Oh, that's a pictorial. That's a very that's taking Feynman's idea of path integral and making it very, very sort of poetic. I don't think about those kind of stuff. So, I mean, because according to Feynman, an anti-electron is an electron going backward in time, right? So a positron is an electron going backward in time. So for example, the picture is that you have an electron going forward in time, and it meets a photon going backward in time, and they collide, and so the electron starts going backward in time. So because we are creatures who are or what happens if the electron is going forward and it emits a photon going forward in time, and then it goes backward. But what we see is that an electron and a positron going forward in time, annihilating and giving rise to two photons. Okay, so in that way, this electron and this anti-electron is the same thing. So the electron can keep doing that, right? This is like, it can keep doing stuff like that, right? And for us mere mortals, all these particles look different, but it's actually the same particle weaving in and out. So I don't think about these kind of things very much, but you can if you want to. I think that's basically the whole thing, is that, yeah. People who like to mix philosophy with their physics think of these things. I've definitely heard of this. The first time I heard of this was from a physicist from Dhaka University. His name is Ahmed Shofi. He's still around, I think, but he's very ill. Okay, any more questions? So if not, thank
no,
you.
But
Yeah.
I wanted to say that philosophy actually means lover of science. So I guess it makes sense.
No, I studied philosophy for 4 years on my own. I mean, it's not like I actually was. There is a philosophy circle in Dhaka. When I was an undergraduate, 3 or 4 of my friends and I, we actually formed a school, like a study circle, and we would go and meet every week with this scientist. His name is Liaquat Ali. He was at Burden for many, many years. He's retired now, and he was basically our guru, and we studied epistemology from the Greeks until the 20th century. So philosophy is something that I really love. And but these are more like this kind of stuff, that the same electron is everywhere, is more speculative for my is too speculative for my taste. It's as I said, it's a matter of taste. I tend not to think about such things.